Hello, students. Have you ever just looked around and wondered, what is everything really made of? I mean, the chair you were sitting on, the water you drink, even the air we breathe. Well, today we are going to begin a fascinating journey into the very heart of matter to understand the fundamental rules that make all of chemistry work. Let's start with a simple thought experiment. Imagine you have a piece of chalk. Now, you break it in half. Then you take one of those halves and break it in half. If you could just keep breaking it into smaller and smaller and smaller pieces, could you do this forever? Or would you eventually reach a tiny, tiny particle that you just cannot break any further? This very question, has puzzled people for thousands of years. And this question was first explored not in a laboratory with beakers and chemicals like we have today, but in the minds of ancient philosophers, both in India and in Greece. What's really fascinating is that way back, around 500 BC, great thinkers in different parts of the world came to a very similar conclusion. In India, a philosopher named Maharishi Kanad suggested that if we keep dividing matter, what he called padarth, we will eventually reach the smallest possible particle. He gave it the name Parmanu. And over in Greece, Democritus proposed the exact same idea. He said there must be a final indivisible particle, and he called it atomos, which literally means uncuttable. But remember, these were just philosophical ideas. They weren't proven by experiments just yet. For many, many centuries, this is where the idea of an ultimate particle stayed. It wasn't until the 18th century that scientists finally began to test these ideas with very careful experiments. You see, this was the big moment when philosophy started its journey to become the science we now call chemistry. The foundation of this new modern chemistry was really laid by a brilliant scientist named Antoine Lavoisier. He is the one who established the very first and most crucial law of chemical combination, a rule that all chemical changes have to follow. And here is that law. It's called the law of conservation of mass. It states a very simple but incredibly powerful fact. In any chemical reaction, mass can neither be created nor can it be destroyed. In simpler words, it means that the total weight of all the substances you start a reaction with must be exactly equal to the total weight of all the substances you end up with. Nothing just disappears and nothing appears out of thin air. So how did scientists actually prove this? I mean, it's not enough to just say it's a law. You have to show it, right? Let's walk through a classic experiment that demonstrates this law perfectly. Imagine this setup. A scientist takes two chemical solutions. Let's call them X and Y. One is in a flask, and the other is in a little tube hanging inside the flask, carefully so they don't mix yet. Then they seal the flask tightly with a cork and place the whole thing on a weighing scale to measure its mass. After noting down that first weight, they tilt the flask, the solutions mix, and the chemical reaction begins. After the reaction is over, they weigh it again to see if anything has changed. Now, let's pause here. Think about this for a moment. Why is it so important to put that cork on the flask? Why not just leave it open? What do you think? Well, the reason is that the cork creates what we call a closed system. You see, in some chemical reactions, a gas is produced. You might see it as fizzing or bubbling. Now, if the flask were open, this gas would just escape into the air. If that happened, the flask would weigh less at the end, and it would look like mass was lost. But the mass isn't lost, is it? It just floated away. The cork traps everything inside, so we can be sure we are measuring the mass of all the products, including any gases. And the final observation is always the same. Every single time this experiment is done correctly, the reading on the weighing scale, it does not change. Not even a little bit. The mass before the reaction is exactly equal to the mass after the reaction. This is a brilliant and simple proof of the law of conservation of mass. Let's look at some actual numbers to make this even clearer. Say we react 5.3 grams of sodium carbonate with 6.0 grams of acetic acid. If we add those two up, 5.3 plus 6.0, the total mass of our starting materials, our reactants, is 11.3 grams. Now, after the reaction, we get three new substances: sodium acetate, carbon dioxide, and water. If we measure their masses, 8.2 grams, 2.2 grams, and 0.9 grams, and now add these up, what do we get? 8.2 plus 2.2 is 10.4, plus 0.9 is exactly 11.3 grams. You see, the total mass is perfectly conserved. Okay, so we've established our first big rule. Mass is always conserved. Now let's look at the second major law. This one deals not with the total amount of matter, but with the specific recipe for how elements combine to make new substances. This is the law of constant proportions. It was given by another great chemist, Joseph L. Proust. In simple terms, this law means that a pure chemical compound, let's say water or salt, will always contain the same elements combined together in the same fixed proportion by mass. It's like a fixed recipe that never changes. The best example for this is water. Now, listen carefully. It does not matter where that water comes from. It could be from a river, from the sea, from the rain, or even water that we make in a laboratory. In pure water, the ratio of the mass of hydrogen to the mass of oxygen is always 1:8. Always. This means for every 1 gram of hydrogen in water, there are always exactly 8 grams of oxygen. That recipe is fixed. Let's take one more example just to be sure we understand this. In the compound ammonia, which is made of nitrogen and hydrogen, the mass ratio is always 14:3. So for every 14 grams of nitrogen, there will always be 3 grams of hydrogen. It's another fixed chemical recipe. This is a very important point, students. This is what makes a chemical compound different from a simple mixture. A compound like water has a fixed recipe, but a mixture like nimbu pani or lemonade does not. You can mix a little bit of sugar or a lot of sugar into your water, right? The ratio can change. So in a mixture, the proportions are variable, but in a compound, they are constant and definite. So now we have these two fundamental laws. One says matter is never lost. The other says compounds have fixed recipes. What do these rules actually tell us about what matter itself is made of? These two laws really became the two pillars on which all of modern chemistry is built. They established clear, predictable rules for how matter behaves when it undergoes a chemical change, giving scientists a proper framework for understanding reactions. And these very strict rules pointed scientists towards a really powerful conclusion. If matter always follows these laws so perfectly, well then, it can't just be some continuous stuff that you can divide forever. It must be made of some kind of fundamental, separate particles. And this idea became the foundation for the next great theory about matter. Which brings us right back to our very first question. But now we have scientific evidence to think about. If mass is always conserved, and if elements only combine in fixed, definite recipes, what kind of tiny particles could possibly explain these laws? This is the question that set the stage for the next big idea in chemistry, which is the atomic theory. Think about it, and we will explore the answer in our next lesson.